Good morning and welcome to iScience Radio. I am your host, Nada Soufi.
iScience Radio.
In anticipation of the new Project Hail Mary movie starring Ryan Gosling, some of us here at the iScience magazine have read the book. We are definitely read the book before watching the movie, people. And having finished the book now, I can finally say that I really enjoyed it. To summarize, the book is about a school teacher turned reluctant astronaut hero. The main character, Ryland Grace, wakes up in a spaceship with no memory of how he got there. Through lots of trials and tribulations, he finally figures out that he's on a mission to save the Earth from a sun-killing microbe. On his journey, he meets a friendly alien, and together they perform science experiments to save their planets. I won't spoil the ending, but I highly recommend reading the book. There was a lot of science in it, particularly some physics that I did not quite understand. So to help us understand the physics, we are joined by Fay Dowker. She is a professor of theoretical physics here at Imperial. Hello, Fay. Thank you for joining us.
Thank you for having me.
So my first question to you, Fay, is have you heard of Project Hail Mary at all? Has it circulated in the physics circles or not yet?
The first time I heard about it was when you contacted me about this interview. So I had a little look at it online and read the wiki page.
Okay, so
but that's as much as I know.
You're brand new to it. Maybe I'll convince you by the end to read it. So one of the concepts in the book that I found quite hard to understand was time relativity or time dilation. So the protagonist in the book, Ryland Grace, travels about 4 years in space, but he says that the people back on Earth have experienced 13 and a half years. How is this even possible?
That's a key concept in Einstein's theory of relativity, that time is not a global concept. It's not some big clock in the sky that ticks away at the same rate for everyone, wherever they are in the universe or whatever they're doing. It just isn't like that anymore. But time in relativity is a local thing. It's a local concept. So you have your own time that elapses for you along your journey through space-time, and I have my local time that elapses for me along my journey in space-time. And our watches, do you have a watch?
Yes, a digital one.
Okay, me too. I have the iconic Casio F91W that does absolutely nothing except tell the time.
Oh, okay.
So I really love it. Every time it breaks, I buy a new one. So these watches that we carry along our own personal, particular journeys through space-time, they're like odometers for time. So the odometer on your car measures the distance in space that your car travels. So if I drive to Manchester, then my odometer will tell how the distance that I've traveled along the roads that I've chosen, and it'll be, roughly 200 miles or give or take. But if you drive to Manchester in your car and you take a different route, then the odometer in your car is going to register a different amount of distance traveled for you.
Yeah.
So watches and clocks are like odometers for time. And if you and I go on different journeys through space-time, say you get in a spaceship and you go off somewhere distant and then you come back, you've traveled in space-time in a different way to me, and your watch will register that a different amount of time has elapsed for you. And it's a different way of thinking. So relativity demands that we take on a different worldview than the one that we have. So the one that we've grown up with, that we're taught at school, that is inherent in Newtonian physics, that is of space, three-dimensional space, and we all move around in it. And then there is this universal time that ticks away at the same rate for everyone. You have to ditch that view and take on the view that there is space-time. That's a four-dimensional entity, four-dimensional fabric, and we have our trajectories and journeys through space-time, and watches and clocks are odometers for time along journeys through space-time. And once you take on that view, it's no surprise that different journeys through space-time should take different amounts of time, and that watches and clocks will register different amounts of time that have elapsed. The strange thing becomes why we don't notice that in everyday life.
Right.
And we don't notice it because although those differences are there, they're absolutely so tiny in everyday life, in our everyday emotions and our everyday experiences of space-time, that my Casio watch is just not accurate enough to register the differences in time between my journey and your journey.
Okay, so it's more about like perception and how we view time.
It's not about perception.
Okay.
Right. So it's a real physical thing. It's a physical amount of time that elapses along your so in relativity we call it world line. So your journey through space-time is called a world line, and it's absolutely physical. It's not to do with your perception. If a robot or some automaton took your watch and moved it along this trajectory, it would measure the same amount of time. So it's not to do with human perception. It's physical.
Okay.
So it turns out that our perception is absolutely anchored to the passage of time. So perception does come into it. But this phenomenon of time being local is not to do with human beings. It's not to do with consciousness. It's to do with a real physical quantity, which is physical time that elapses along these trajectories or world lines in space-time. And those world lines can be world lines of human beings, they can be world lines of a computer, they can be world lines of your cat. It's not to do with the particular thing that is moving along this world line.
Okay. Wow, it's a bit mind-blowing to kind of shift your idea of what time is.
It is. So we have to unlearn a whole bunch of stuff that we've learnt since we were at school. But it's kind of interesting that apparently small children don't have this concept of a universal time that is the same for us here and people right now in Australia, or people, or let's say aliens, hypothetical aliens on some planet orbiting some star in some distant galaxy, right? The idea that there's a notion of right now for everybody everywhere in the universe is not something that small children are capable of comprehending. They tend to think of time or conceptualize time as orderings of events and durations which are personal to them. The idea that there's some other distant place where there is a notion of right now is something that they have to be taught. It's not something that they know through their experience. And this is something that psychologists, early years psychologists, have studied, and they've done studies about how children think about time, how they think about how they conceptualize time. So in fact, we have been taught that there's this universal time. We've been taught that there's such a thing as right now in Japan. We've been taught that there is this universal clock ticking away for everyone and everything. We've been taught that, and that's the basis of a lot of physics, Newtonian physics, a lot of science. But that's not the case in relativity, which is a new and better way of understanding space-time. There isn't this universal notion of now, right now, across the whole universe. There is local time, local to us, and it's the idea that there's this simultaneous events distant from us, far away in the universe. That just isn't there in relativity. It's a notion that you have to chuck out the window, and when you take on this new perspective, which is a perspective of there being a four-dimensional reality, four-dimensional space-time.
And you work a lot on space-time. What drew you to it and trying to shift your ideas about it?
When I went to uni, I went to study maths, and I was a complete maths fanatic. I studied double maths and physics for my A-level, and if they had let me, I would have studied triple maths instead. I didn't really like physics when I was at school. But when I got to university, and in my third year, I think, I took a course on general relativity, Einstein's theory of space-time and gravity. And I thought, I really like this. and I just want to know more about it. And that feeling has never gone away. So I fell in love with it then, and I still love it now. And I wanted to know everything there was to know about space-time. But then I realized that there were people who were working on a deeper theory than general relativity. And I thought, that what could be cooler than that? So not only is general relativity this mind-blowing new perspective on reality, we believe, a lot of people believe, that it's not the final answer. There are lots of questions that general relativity cannot answer. For example, it can't answer the question of why the universe started off the way it does, why we think that it started out in this hot, dense state and it exploded outwards in this event that people call the Big Bang. But what came before that? Or how did the universe get to be in this hot, dense state? Those questions are unanswerable using general relativity. So people are seeking a new and deeper theory, from which you could derive general relativity. General relativity should come out of that deeper theory, but it's not. There are lots of scientific, interesting questions that GL cannot address. General relativity cannot address.
I want to shift us back to science fiction. I know you also worked on wormholes, and they've been depicted a lot in science fiction. How do you feel about these theoretical concepts being portrayed in science fiction? Are they inaccurate, or are they opportunities to spark curiosity?
I think they're both those things. Sometimes they're inaccurate. Sometimes movies try really hard to depict things as best they can, knowing and incorporate known science and incorporate more realistic depictions of scientific theories. So there's a wide range of different ways that movies and science fiction deals with science, and that's good. That's fine and fun. And also it does spark curiosity, and it does encourage people to think and enjoy scientific ideas, and it can also be inspiring in other ways. So one book that I really enjoyed when I was a young girl, is A Wrinkle in Time, which is a lovely children's science fiction book, and the protagonist is a girl, and she's a kind of nerdy girl. She likes maths, she likes science, she's got scientist parents. She doesn't really fit in at school, and she's kind of a flawed. She's a great character because she's not perfect. She's flawed in many ways, but she is brave, and she has these adventures which are fun and introduce interesting ideas. So that kind of thing can also happen through science fiction.
Okay, so you're not too worried about the inaccuracies in science fiction, more that it's just fiction. A fun way. Yeah. No, people do know it's fiction.
The whole point about fiction.
Yeah. But these are theoretical ideas, so they're really hard to depict. I know you've mentioned Wrinkle in Time, but have you ever come across a piece of sci-fi that depicts things in a way that you think is possible or probable, or has it always been like, oh, we just don't know, it's just a fun way of depicting it?
I think it can stretch your brain and stretch your mind and make you think that things are more or less possible. So a nice example that I like to bring up is Bill and Ted's Excellent Adventure. It's a bit of an old... You're too young to know. Bill and Ted. But it's about time travel. But it has lots of jokes in it about the sorts of things that you would have to think about if you did have a time machine that was able to transport you into the past and then back again into the future. So there's a scene. Can I describe this scene?
Of course you can.
Yeah. So my favorite scene in Bill and Ted's Excellent Adventure is when Bill and Ted have this time machine. It's like a phone booth thing. And they have to write a history report, otherwise they're going to flunk out of school. So they go back in time and they kidnap these historical characters that they're going to bring to their school report, project report, final show, and that's going to allow them to
give
pass
them an A+.
Exactly, to pass their course. So so they bring them back to to their time in California, and the historical characters are they're arrested by Ted's father, who's the local sheriff, and put in jail. Right, so they're in jail, and they've got to break them out of jail. Bill and Ted have to break out these historical characters out of jail, and they think, oh, if only we could, what we could do? We could go back in time using the time machine, and we could steal your dad's keys, and we could leave his keys to the jail for ourselves here to find. And then they say, okay, well, where would we leave them? He said, what about behind that sign? And so they look behind the sign, and there are the keys.
Wow.
All right.
Yeah.
And then they say, oh, but dude, we've got to remember, when all of this is over, we've got to remember to go back in time and steal your dad's keys. And then they think, but we already did. So, So it's a joke.
Yeah.
And apparently, so I talked to one of the script writers, I think. I had an opportunity to do some outreach event at the Science Museum, which was talking to Alex Winter, who's one of the actors and who plays Bill, and the scriptwriter. And the scriptwriter said, oh, we filmed that scene and the whole of the rest of the remaining scene where they break the characters out of jail because we had no budget for special effects. So we had to do everything in this kind of jokey way, just because there was no money. But what happened was that they made this fantastic joke, which is also something kind of deep, which is,
of course, yeah.
If you could do that sort of thing, then what you do in the future is entirely determined, because they found the keys, and therefore in the future they have to go back in time and steal the keys, because they did steal the keys. So as far as they're concerned, right at that moment, that's going to be in their future, but they have to do it because the consequence of them doing it is right there.
Yeah. So it kind of proves it. Yeah.
Yeah. So anyway, I like that film just because it's a funny film, but it also involves these thoughts that you have to have if you're going to consider the possibility of time travel in physics. So
of course, that's a great example. I feel like I definitely have to go check that one out. As a science communicator, I wanted to ask you, how do you approach communicating like physics concepts like these? You've mentioned some great examples, but these are, fictional and for fun. But as a researcher and a scientist, how do you approach communicating these kind of hard to grasp concepts to maybe like a regular person who doesn't have a groundwork of physics?
I like to try to relate it to people's experience. There's this idea that physics is beyond our experience, that particularly current modern theories of theoretical physics don't accord with our intuitions about the world, which we gain through everyday experience. And to a certain extent that is the case, but it can't be completely the case, because all we have to go on is experience. So all of the evidence for our scientific theories is gained through experience. That's what we have. So our theories must accord with our experience. If they don't accord with our experience, in some sense, then they can't be right. There's this, what I call the empirical demand of science, which is you can't just invent any old thing. You have to test it, use it, and what do you test it with? Well, it has to coordinate with your experience. And of course, in science, that experience involves very precise measurements and outcomes of experiments and the input of a whole community. So it's the notion of experience is very rich. But nevertheless, the scientific theory has to be consistent with experience. It can't contradict experience, because experience is what we base our understanding and knowledge on. If we didn't have any experiences, there wouldn't be science, right? So I like to try to bring people in by appealing to their experience.
Okay.
So I have this playbook which I use to explain to people a particular aspect of general relativity, which is that there is no force of gravity pulling you or me down towards the center of the earth right now. It doesn't exist. There is no such force. And the thing is that if you think about it, I claim, a little bit, if you concentrate on what you actually feel, you can't feel such a force.
Yeah. No.
What you feel is your chair. You and I are both sitting down, so we feel the seat of the chair pushing
Pressure.
up,
Yeah.
pushing up on us.
Yeah.
You don't feel anything pulling you down. And the reason you don't feel anything pulling you down is because there is nothing pulling you down. That's one of the revelations that Einstein had, that he called it essentially the happiest thought of his life. He realized, oh, there is nothing pulling me down. There's just my chair pushing me up.
Yeah.
And that's something that everyone can experience. And so they're experiencing something which is a key part of the development of general relativity. So, but they can just experience it right here, right now.
Wow.
Sitting in their chairs. So, that's one thing I like to try to do when I'm talking about physics that might seem very far away, very distant, bit abstract. So just anchor it in people's experience.
Yeah. No, I think that's a great way to do it. I almost feel like I'm about to float out of my chair right now, thinking that nothing is dragging me down. What are you working on now? We've talked about space-time, and I know you've worked on wormholes as well, but are you still in the space-time, or are you looking at something different at the moment?
Yeah, I'm still into space-time. I'll be into space-time forever and ever.
Forever and
ever. Yeah. That's it. That's my home in physics. So I am pursuing a particular approach to what people call the problem of quantum gravity. So general relativity, which is our theory of space-time, is also a theory of gravity, so that two things go together. And I said that there are questions that we have about the universe that general relativity can't answer, such as what happened before the Big Bang, or was there even a beginning before? Was there even anything going on before the Big Bang? And where general relativity breaks down is where, in precisely the scenarios where you can't ignore quantum theory, the quantum physics that we know describes the matter in the universe. So our theory of space-time, general relativity, can't cope with, it can't accommodate very highly quantum matter. So matter that is very, very dense, very hot, exactly the conditions that you find at the beginning of the universe, at the Big Bang. Okay. So GR just breaks down there. So we need a theory of quantum gravity, something that can cope with, can accommodate this quantum nature of matter, and also applies to space-time and to gravity. And I pursue a particular approach to that problem, which is called causal set theory. In that approach, space-time is hypothesized to be fundamentally discrete or granular. It's not smooth and continuous, but is made of individual elements, space-time atoms. And it's a speculative approach. It makes certain postulates about what's really there, what's really going on, what space-time is really like underneath in its deep structure. And so I'm working on how we might test that theory, how it would appear to us, because the scale of this discreteness is really tiny.
Right.
And it's just beyond what we can directly probe, but maybe it has some indirect effect on things we can see.
Sounds very interesting. I feel like I've learned a lot more physics today than I've ever have. Just to finish us off, a fun question for you. In the movie, there is a little fun alien. He's very sassy. He's my favorite part of the book. From your perspective in physics, do you think extraterrestrial life is possible?
There's no obstruction from physics to the existence of life elsewhere in the universe. It's one of I think there's a famous, I don't know who said this, but if you ask the question, is there life elsewhere in the universe, or are we alone? Someone made the comment that either answer to that question is mind-blowing. So either we're alone, and the universe is extraordinarily big. You know, there are 100 billion stars in our galaxy, and there are 100 billion galaxies in the observable universe. So it's mind-blowingly big. And the idea that there's just us in that vastness is, you know, it's like fall off your chair.
Yeah.
Astonishing. But to think that we're not by ourselves and that there are other beings out there also is fall off your chair, exciting as well. So
Both
and
ways,
interesting.
yeah.
So both answers are equally kind of amazing to contemplate.
Wow, amazing. Have I convinced you to read the book or watch the movie, Faye?
I would love to read more. I have a pile of books by my bed, which you know, I would just love to have time to read more. So maybe I'll get the book and put it in the pile. Whether I'll actually get to read it, I don't know.
That is fair enough. You are a busy physics researcher. I completely understand. I hope you do get to it because it is a fun read. But thank you so much for joining us today in the studio to tell us all about your research and physics in general. I hope you enjoyed listening to this episode of iScience Radio. I was your host, Nada Soufi, and produced by Isabella Fraser.
iScience Radio.